So we finished up there, introduced this concept of using double integrals. This is how I solve these problems. Let me show you how this works. Seriously, if this is the first time you've seen double integrals, I know it's a bit scary. I get that. Well, let me show you how this works, okay? Let's say this is my example. Let's say that I've got, very simply, the function. So this is my shaded area here. And let's say that this is my function here, y is equal to x squared. That's my function. And we're going to go up to a value of 1 on the y-axis and 1 out here on the x-axis. Y. And we want to find the centroid of the shaded area. Okay, find the centroid of the shaded area. All right, we've already introduced this concept here. Okay, so if I want to find the x bar, that's going to be the integral, double integrals. It's going to be the integral x dx. I'm sorry, dy dx. So integral x dy dx. Okay. The inside integral is along the y-axis. So the y-axis, we're going to go, one might look at it and say, well, Steve, I'm going to go from 0 to 1. Well, no, actually, at different values of x, you're going to go from 0 up to whatever this y is here. And that's what we're saying here. We're going to go from 0 up to whatever y is. So I'm starting at 0 in this case. Now, if I have something else below here, maybe I don't start at 0. Maybe I've got -3, or maybe there's another function down here. So I would actually be between two functions. But here, I'm starting at 0, and I'm going up to whatever this function is. Well, in this case, the function is x squared. Right? And if sometimes I find it might be helpful to write this out as y is equal to x squared. But you could just write it as x squared if you like. And on the outside integral, I'm integrating with respect to x. So along x, I'm going from 0 all the way out to 1. And you might say, well, Steve, why isn't it 0 to y? Well, because, again, this is the outside integral. I've already said, well, I'm going up to this different height, but I'm doing it across this entire x spectrum. So I'm going all the way from 0 all the way out to 1. And each individual y value along the way is going to get integrated and rolled up in there. And then the bottom integral is just going to be, again, it's double integral dy dx. So integral dy dx. The outside integral, the limits are the same, top and bottom. The outside integral is going from 0 to 1. The inside integral is going from 0 up on the y direction up to whatever the y function is, x squared in this case. Okay, so we can work both integrals here. We'll work them simultaneously. So here's what happens when I'm integrating one variable with respect to the other. If I'm integrating one variable with respect to the other, I'm going to treat the other variable as a constant. So if I'm integrating x with respect to y, it's very simple. I just treat this x, or if it's x squared, or whatever it might be, I treat this as a constant. So to evaluate the inner integral, I'm going to leave the outside integral alone. I'm going to go from 0 to 1 on the outside. We'll go ahead and evaluate the inside integral. So I'm integrating a constant with respect to y. So I'm just going to take that constant, multiply it by y. Integral of any constant with respect to y is just that constant times y. And I need to evaluate this integral from 0 all the way up to this x squared. I'm going to say 0 all the way up to, I like to say y is equal to x squared. So I remember, oh, this goes in for the y value. And so this is the inside integral. We've evaluated it, and it needs to, then the outside integral is still there. We haven't done it yet. So that's, I need to integrate with respect to x once I'm done here, once I've simplified this. And I'll do the inside integral also on the bottom. So leave the outside alone. I'm going to again integrate from 0 to 1 for the outside integral. Here I'm integrating with respect to y, just integral dy. Well, that's just y. So I'm integrating, I've got y, and that needs to be evaluated along these limits from 0 up to y is equal to x squared. Or you could just write x squared there if you can remember this is going in for the y value. This one's pretty simple. And at least the bottom's pretty simple. And again, I haven't touched the outside integral, so I need the limits on one side. I need dx on the other. Okay. I'm going to go on to the next line here. I can probably get it done down here, but let's go on to the next line. Okay. Let's evaluate this integral now. So I've got it kind of written in notation here. Let's simplify it out. So let's leave the outside integral alone. We still need to do that. I'm going to plug in for the y here, I'm going to plug in x squared. So it's going to be x times, plug in x squared here, x times x squared, and then minus, I'm going to plug in 0 for y on the other one. So it's going to be x times 0. That's easy. I haven't done the outside integral yet, so I need to leave it alone. So this one's not too bad so far, right? The bottom, leave the outside integral alone if you like. We'll do the same thing here. I'm gonna, I need to simplify this notation here. So I'm gonna plug in for y, x squared, and subtract from that where we plug in the lower limit, plug in 0, and that's going to get integrated with respect to x. Skip as much of the steps here as you're comfortable with. This is obviously on top. I'm going to be integrating from 0 to 1 x cubed. This is x squared times x. And this is 0. So x cubed minus 0 is just x cubed. That needs to be integrated with respect to x now. And the same thing in the bottom. I'm going to integrate from 0 to 1. This is x squared minus 0, so it's just simply x squared dx. Okay? And then I need to perform this integral. So on top, I'm going to have the integral of x cubed is just going to be x to the 4th over 4. And that's going to go from 0 up to 1. And on the bottom, I'm going to have the integral of x squared. That's going to be x cubed over 3. And that's also going to go from 0 to 1. Okay, so what do I get here? I get x bar ends up being, I've got basically 1/4 divided by 1/3. Complex fractions tells me that is 3/4. Steve, what the heck does that mean? That means I found x bar, the x location of this centroid, is going to be 3/4 of the way between 0 and 1 here on the x-axis, in here somewhere, which makes sense. This is the thickest part of it. This is where the most mass is located. This is most likely where the center of mass is going to be, somewhere in this thickest part of it. So with the x location, we've just found it to be 3/4. Let's do the same thing, but now we're going to use y to find the y bar. So let's go find y bar, shall we? So y bar, if I use back up here in my notes for my template, I'm going to integrate. The inside integral is going to be with respect to y. The outside integral is going to be with respect to x. The top is going to be, I'm going to integrate y. And the bottom, I'm going to do the same thing I did here, which, by the way, you've already found the bottom. This bottom integral, integral dy dx, from 0 to x squared and 0 to 1, is 1/3. So you've already found it. You don't have to redo it. Okay? So we just have to do the top integral now. So yay for that being simpler. I'm going to integrate along x. I'm going to go from 0 to 1. Along y, I'm going to go from 0 to x squared. For the y bar, I need to integrate y with respect to y and then with respect to x. And again, the total area, that's this denominator we found for the x bar, that doesn't change for either one. It's the same. It's 1/3 on both of them. The total area of this shape we've found through calculus to be 1/3. Okay, let's do the top integral, shall we? I'm going to integrate y with respect to y for the inside integral. Let's leave the outside integral alone, just like we did earlier. So we're integrating from 0 to 1. This quantity, I'm integrating y with respect to y. That's going to be y squared over 2. Y squared over 2, and that's going to go from 0 up to x squared. And then I still need to do the inside integral. I'm sorry, I need to do the outside integral, so I still need to integrate with respect to x when I'm done, when I've simplified that. The denominator is still 1/3. All right, I think I could maybe squeeze this in here. So I'm still on top. I'm integrating from 0 to 1. Let's simplify this notation here. So I'm going to plug in x squared first. It's going to be, for y squared, I'm going to plug in x squared. So I'm going to have x squared squared. That's going to be x to the 4th divided by 2 minus 0 divided by 2. And that needs to be integrated with respect to x. And that's over 1/3. So you can see the 0 goes away. I'm now going to be integrating x to the 4th over 2 with respect to x. It's going to be my next step. Do that. Lecture 17. This is going to be page 5 of something. Okay, what do we got here? So I'm integrating x squared over 4 with respect to x. So y bar then is going to be, so this integral here, this becomes x to the 5th over 10, right? Because it's x to the 5th over 5 multiplied by a half. So it's x to the 5th over 10. And that's going to be evaluated from 0 to 1. That's my limits of integration here. That goes down there. And then the bottom is 1/3. So plug in 1, I get 1/10 over 1/3 minus 0 over 1/3. So that goes away. Now I'm left with 3/10. So G, my center of mass, is going to be my x bar, which we found to be 3/4. And my y bar is 3/10, 30% of the way up between 0 and 1. So does that make sense? Well, I'm saying my centroid is going to be probably in here somewhere at 3/4 and 3/10 or 0.3. This would be about where my center would be. That makes sense. It's going to be in here somewhere. Right? Less than halfway up, and more than halfway out here, 3/4 out there. That makes sense. At least to me, it kind of makes sense. We've shown it mathematically. Yay, calculus. It works. If you're allergic to calculus, I'm not sure you're in the right place, to be honest with you. I understand this is double integrals, and you haven't seen those before. Again, very simple. When I'm integrating x with respect to y, I just treat x as a constant, and this just becomes xy. And then now I've got, you saw what happened. Then I've got x cubed. I just need to integrate x cubed with respect to x, and that's just a simple early calculus problem. Okay. I like this a lot better than I do this idea of finding, y tilde is this, and then dA, substitute in for dA, dx, y dx, and I mean, that works. You're welcome to look at the example problems where he does that in the book. I find this approach a lot better. Once you get kind of over the initial gag reflex of the double integrals, I get that that's pretty strong. But here we are. Okay. All right. That's a nice simple calculus example. I can go ahead and let's mention here. I'm going to pause and grab my book real quick. All right. So for common functions, so you don't have to do the calculus every time. Some common functions. If I've got some function that comes up to, on the y-axis, some height h and goes out on the x-axis to some base b, if the function is just a second-order parabola like this, to where y is equal to h over b, it's going to be h over b squared x squared. That's the way that function's going to, that's going to be the structure of that function. Then the area is going to be 1/3 of whatever the product of b and h is. That'll be my area. That's the denominator. Okay. And then my x bar is going to be located at 3/4 of whatever b is. And my y bar is going to be at 3/10 of whatever h is. And that's interesting. Now, hey, calculus, it worked, right? My area, that's my denominator. This is my area. I found that to be 1/3 of the product of 1 times 1. That made sense. My x bar, we found to be 3/4 of 1. And my y bar, we found back over here, there. My y bar I found to be 3/10 of h, which is 1. So for any shape, any parabola shape, you can do the calculus. It's good practice, but you are welcome to employ this function. We've done the calculus once. For any parabola like that, you're welcome to employ this function. If I continue on, we look at, well, what about other orders, Steve? If it's a third order polynomial, going out from 0 to b on the x-axis, and I go up 0 up to h on the y-axis, and again, this shaded area, if this is for between the function and the x-axis. It flips a bit for the y-axis. We can talk about that in a second. But if this is what we got, y is equal to, and this would be the structure, would be h over b cubed x cubed, then the area ends up being 1/4 of the product of bh. The x bar location is 4/5 of whatever b is, the base is, and y is going to be 2/7 of whatever h is. And so a pattern emerges if you continue doing the calculus out, and people have already done these, so we don't have to. So we don't apply the logic out, and we say, okay, well, isn't there a pattern? Yes, there's a pattern actually emerges. So the pattern that emerges is for any polynomial, y is equal to h over b to the power n, x to the power n, then the area ends up being 1 over whatever n is, the order of the polynomial, plus 1 times bh. That's what the area ends up being. So if it's a second order, it ends up being a third order. It's 1/3 if it's a parabola. It's second order parabola. It's 1/4 if it's a third order parabola, etc., etc. X bar ends up being located at n plus 1 over n plus 2 times whatever the base is. And the y bar ends up being, the pattern here is a little more complex. It's n plus 1 over 2 times 2n plus 1. And that's times h. So that's for any parabolic shape following this pattern. I shouldn't say parabolic. I should say any polynomial, any power term following this pattern. You're welcome to employ this generic formula for it. Okay. Now, I should mention real quickly here, and I'll quit this video and we'll move on to the next one. I should say if this is what we have. So I mentioned earlier, we've looked at, all right, what if it's the shaded areas between the x-axis and the function? What if, though, the shaded area is between the y-axis and the function, but it's the same pattern? We'll go out b base on the x, and we'll go out to a height h on the y. Well, this would be the same. So if this is y is some function of x, y is some function of x, well, I could treat it, I could basically flip the axes. What is an x-axis? Why does x have to be left to right? Why can't x be up and down? It could. So I could treat it kind of the same way. I could say x is going to go 0 up to b, so we keep it the same, and y is going to go out 0 out to h. And now I would be integrating, or I would be evaluating some g function, where g is x is a function of y. Okay. This would work, and then what I would do is again, I prefer the double integral method, so I'd be integrating from 0 to h on the outside, because it's going to be the y values, and on the inside I'd be integrating from 0 up to whatever g is. For the x bar, I'd still be integrating x, but now I'm going to be integrating with respect to x and then with respect to y. So where earlier I integrated with respect to y first and then with respect to x, I flip them if it goes the other direction. Right? And the same thing on the bottom, it's 0 to h, 0 to whatever that g is, this function here. And then I would do dx, dy. And the same thing for the y bar. follows the same basic structure. 0 to h, integral 0 to g, y dy, dx dy, over integral 0 to h, integral 0 to g, dx dy. Now for me, I'm not going to assign or test you on one of these where it's, I'm only going to worry about the shaded down to the x-axis. If you understand that and you do the calculus on that, you can figure this out if you need to. Our focus is really going to be more on the composite bodies, which we'll discuss here very soon. I'm going to stop this video here, and I am going to show you one more video, or at least talk about working between. I guess we could do it. It's okay if this video is just a bit long. So I am going to stop here, and we'll make the next lecture then is going to be composite bodies. So the latter half of chapter 9 for us. So this is going to be lecture 17, and this will be this is going to be page 6. This will be the last page for this lecture, so it'll be page 66. Let's say centroid between two functions. All right? So if I want to find the centroid between two functions, y, x, let's say I've got something going out like this on top and maybe like this on bottom, and I need to find the centroid of this shaded area where I've got some y2 on top, that's going to be some function of x, and some y1 on bottom, also some function of x. And again, we'll go out 0 to b on the x-axis for base, 0 to h on the y-axis for height. So again, the area here is going to be the integral from 0 to b, integral from y1 on the bottom up to y2 on top, and we're going to integrate dy dx. Much like we did previously. It's the same way we found the denominator on the previous problem. But the difference is instead of going from 0 up to y, here I'm going, the bottom limit is this y1 function, and the top limit is this y2 function. So this is how we'd find the area. Our denominator for the expression, x bar, I would find as the integral from 0 to b, and the inside integral is from y1 to y2. I'm going to integrate x with respect to y first, and then integrate that result with respect to x. Divide that by this area, which I find over here. And the same thing for y bar, similar thing for y bar. From 0 to b for the x limits, y1 up to y2. For the y limits, we're going to integrate y with respect to y first, and then second with respect to x. Divide that by the total area, and that will tell you where the centroid G for this thing would be at some x bar and some y bar. Okay? All right, we'll pick up there. Like I said, we'll start composite bodies for lecture 18.